What if the entire universe, everything you see around you, isn't really made of particles and energy, but of, well, pure computation? Today, we are diving deep into a truly mind-bending idea that could completely rewrite how we understand everything, from a single snowflake all the way up to the entire cosmos. For centuries, we've pretty much assumed that the deepest truths of reality are written down in these elegant mathematical equations. But what if that's just not the whole picture? What if the universe is actually running on a totally different kind of operating system? All right, to really get our heads around this, here's our game plan. We're going to start with the main idea, this concept of a computational universe. Then, we'll get into the fundamental no shortcut rule that makes it all tick. After that, we'll see how nature uses this system almost like a search engine. And finally, we'll explore what this all means for the code of reality itself and, our place in it. Okay, let's jump right into the first big idea. To really understand this new kind of science, we've got to start with a huge shift in how we even think about the universe. And this is the absolute key. The theory isn't just saying the universe is like a computer. That's not it at all. The claim is that it is a computer. Everything we see, from biology to the laws of physics, is just the output of this massive, ongoing computation. So how does a universal computation like this even work? Well, what's so wild is you don't need some super complex blueprint to get a complex result. Nope, all it takes is a really simple rule that just gets applied over and over and over again. A single instruction, repeated millions of times, can create patterns that look incredibly intricate, totally unpredictable, and maybe even alive. So this idea that simple rules can create all this complexity, well, that leads us straight to a really powerful concept. One that helps explain why so many things in our universe feel so stubbornly mysterious. This right here is the golden rule of this whole thing. It's called computational irreducibility, and it means exactly what it sounds like. For a whole bunch of systems out there, you can't just solve an equation to figure out what's going to happen next. You can't just skip to the last page of the book. The only way, literally the only way, to find out what happens is to actually run every single step of the computation. So the process just unfolds one step at a time. You start with a simple setup, you apply a rule, and you get a new setup. Then you apply that same rule to the new setup, and on it goes. There is simply no way to know what step 500 is going to look like without first going through all 499 steps that came before it. And all of a sudden, this one idea starts shining a light on so many different fields. It helps us understand why an AI's neural network can be so powerful, but we can't really explain how it works, why it's a black box. It explains how evolution can produce something as mind-bogglingly complex as a human eye without some grand designer. See, these systems aren't just random. Their behavior is computationally irreducible. Okay, so if nature is running a computation, how does it find the right programs to build things like us? Turns out it's a lot less like a careful architect and a whole lot more like someone just digging for gold. Oh, I absolutely love this analogy. When we humans engineer something, it's like we're building with perfectly neat, uniform bricks. We design all the parts to fit a specific plan. But biology and AI, they do something completely different. It's like they're searching through this giant pile of weird, irregular rocks, all the possible simple programs out there. And they just keep trying them out until they find a combination that just so happens to build a sturdy wall. And that's exactly why the results can seem so clever and yet so alien to us. They aren't built on principles that we would recognize as good design. They're just the programs that happen to work, discovered through this massive, cosmic scale game of trial and error, searching through this whole universe of possible computations. All right, now let's take this idea to its absolute most mind-bending conclusion. If everything around us is a computation, what does that actually mean for the fundamental fabric of reality itself? So the proposal here is, it's really out there. Forget what you learned in physics about space being this smooth, continuous thing. This theory suggests it's actually made of a gigantic, but finite number of separate points. You could call them atoms of space. And what we experience as physics is just the network of relationships between these points, updating over and over, step by step, according to some incredibly simple fundamental rule. And this leads us to the ultimate concept, the Ruliad. Okay, try to imagine not just our universe's program, but every possible program that could ever exist, running with every possible starting condition, all at the same time. The Ruliad is this infinite, tangled-up object that contains all of those computations and all of their histories. In a weird way, it's the ultimate map of everything that is computationally possible. So, if we're living inside this vast Ruliad, this universe of all possible computations, then why does our reality look the very specific way it does? Why do we have consistent laws of physics, like gravity? Well, the answer might not be out there in the universe, but right here, inside us. As observers, we have two really important properties. First, we are computationally bounded. We can't process an infinite amount of information. And second, we have this deep belief that we persist through time. We see ourselves as this continuous story moving through history. And this leads to maybe the most radical takeaway of this whole thing. The laws of physics that we observe, things like the arrow of time or the weirdness of quantum mechanics, they might not be fundamental features of the universe at all. Instead, they could just be the natural consequences of our specific, limited way of looking at it. They're the patterns that emerge when a finite mind, like ours, tries to make sense of an infinite computational reality. Which leaves us with one last profound question to chew on. If the reality that you experience every single day is just a kind of user interface that's been simplified for observers like us, then what does the raw, underlying reality actually look like? What is the universe's source code? Now that is something to think about.
Welcome to the debate. Today, we are examining a pretty provocative central theme derived from Stephen Wolfram's The Computational Architecture of Universal Complexity. We are framing our discourse around a profound disagreement. Is the universe literally composed of discrete computational rules at its fundamental level? Or is computation merely a highly effective framework, a map, if you will, for understanding irreducible complexity in systems like biology and artificial intelligence?
Right, and this discussion emerges directly from Wolfram's material regarding how very simple rules can generate astonishing complexity across biology, machine learning, and fundamental physics.
Exactly. I will argue that reality actually is computation, and that fundamental physical laws, including entropy, are merely reflections of our limitations as observers embedded in this computational universe.
And I will argue that while computational irreducibility brilliantly explains complex, evolved systems like AI and biology, taking the leap to claim space itself is discrete and that physics is purely an artifact of observer limitation is a profound overreach that conflates a model with fundamental reality.
Let's start by unpacking the sheer scale of the paradigm shift proposed in this material. I remember the first time I really wrestled with this. It feels deeply counterintuitive to let go of the elegant continuous equations we've used in physics for centuries. The traditional view assumes the universe is governed by smooth, solvable mathematics. But the thesis here is that the universe isn't just described by math, it fundamentally is computation.
It certainly shifts our perspective on complexity, I'll give it that.
It does. And at the heart of this is a concept called computational irreducibility. This is the reality that for many systems, you absolutely cannot shortcut a process to predict its outcome. The only way to know what happens is to let it run, step by step. There is no, elegant equation that allows you to skip ahead. It elegantly explains why there is no simplified explanation for complex systems, effectively bridging the gap between how evolution produces intricate biology and why physics looks the way it does.
Well, I want to acknowledge the deep utility of Wolfram's computational irreducibility right out of the gate, specifically when we talk about mining the computational universe. I mean, when we look at machine learning or evolutionary biology, we are looking at processes that search through a vast space of possible programs. I completely agree with the text analogy that biology and artificial intelligence build walls from irregular rocks that just happen to fit perfectly together, rather than engineered, neat bricks.
The irregular rocks analogy perfectly captures why we struggle to reverse engineer these systems.
It really does. But here is the crux of my disagreement. Applying this framework to biology and neural networks makes complete sense because those are, by definition, systems trained or mutated over time until something works. However, applying this to the fundamental structure of reality, claiming space is discrete, and introducing theoretical structures like the Ruliad is an unwarranted leap. Just because natural systems appear random and lack simplified, solvable explanations does not mean space itself is made of discrete computational atoms.
That's an interesting point, though. I would definitely frame it differently. I don't view it as merely a tool for modeling. The material makes the compelling case that natural systems only appear random to us, precisely because their underlying rules produce irreducible complexity. They don't lack rules, we simply cannot shortcut them. Imagine looking at the quantum vacuum or the seemingly chaotic movement of fluids. Traditional physics kind of throws its hands up and introduces intrinsic randomness or statistical approximations. But this computational framework argues that this apparent randomness is entirely deterministic at the lowest level.
But deterministic in what sense?
In the sense that it is the steady, unyielding application of simple rules generating complexity that we, from our limited vantage point, misinterpret as random noise. Think about a neural network. It is a fully deterministic system that produces outputs we cannot reverse engineer. It perfectly illustrates how a rule-based system generates profound complexity without needing a mystical or purely random component. If that is true for AI, why should the fundamental universe itself be any different?
I'm sorry, but I just don't buy that. Let me tell you why. If a system is computationally irreducible, meaning it cannot be shortcut, predicted, or explained simply by an observer, claiming that it is secretly governed by underlying deterministic rules is functionally no different than it being fundamentally random. In empirical science, a distinction that makes no observable difference is no distinction at all.
I'm not convinced by that line of reasoning, because it assumes our current inability to decode the complexity means the underlying rules just don't exist.
But look at the substrate. Yes, computational irreducibility perfectly explains our inability to interpret the black box nature of neural networks, but a neural network runs on an actual computer. It runs on a substrate we built using discrete silicon transistors. The universe does not have a confirmed substrate of discrete silicon. To say that the universe's unpredictability proves it is a computation is a logical fallacy. It merely proves the universe is incredibly complex. Where is the physical computer that the universe is supposedly running on?
That is exactly where the framework gets fascinating, because the material provides a very specific structural proposition for this substrate. We don't need a giant silicon computer in the sky. The proposition is that space itself is discrete, not continuous. The universe is composed of relationships between atoms of space. These relationships evolve through rule-based rewriting. This isn't just an abstract idea. It is a fundamental reimagining of geometry and physics.
And this brings us to the concept of the Ruliad, correct?
Precisely. To help visualize it, think of the Ruliad as an infinite, entangled web of every possible computational rule executing every possible state. Every conceivable rule-based process is occurring within this singular ultimate structure. We as observers are just a thin slice through this vast mathematically necessary object. We experience a specific set of physical laws because of the specific slice of the Ruliad we occupy, and our limitations in perceiving the rest of it. This isn't functionally identical to randomness. It is the ultimate unification of all possible determinisms.
I come at it from a different way. The proposition of the Ruliad actually highlights the philosophical contradiction of this entire framework. On one hand, the material argues that we are fundamentally limited observers, trapped in a tiny, computationally irreducible slice of reality, completely unable to decode the vast complexity around us.
Yes, that limitation is central to why we experience the laws of physics the way we do.
Right. Yet on the other hand, it proposes the existence of an absolute, discrete, objective structure, the Ruliad, which contains all possible computations. If we're just a thin slice, and if our defining characteristic is our inability to shortcut or decode the underlying computation, proposing the absolute existence of the Ruliad assumes a level of objective, God's-eye knowledge that our very position as limited observers should strictly preclude.
I don't see it as a contradiction at all. It's a logical deduction.
But how can you simultaneously claim that our physics is entirely constrained by our computational limitations and then confidently declare you know the ultimate, discrete structural foundation of all reality? It places a framework on the universe that we could never empirically verify precisely because of the limitations the framework itself imposes on us.
I see why you think that, but let me give you a different perspective on the role of the observer, because the material explicitly links our limits to the physical laws we observe. It doesn't claim we step outside the Ruliad to view it. It claims that our physical laws are the inevitable consequence of our limits inside it. The text argues that two specific traits define us as observers. First, we are computationally limited. And second, we believe we persist through time.
And you are saying those two traits generate our physics?
Exactly. It is exactly because of these two constraints that certain physical laws become inevitable from our perspective. Take the second law of thermodynamics, the inevitable increase of entropy. In traditional physics, entropy is often tied to fundamental randomness and the loss of order. But under the computational architecture framework, entropy increases simply because we cannot decode the underlying computation.
So it's an illusion of our minds.
Not an illusion, a matter of translation. The universe isn't becoming more disordered, it is just executing rules that generate computational irreducibility, pushing the system into states that are too complex for our limited minds to reverse engineer. Therefore, the physics we write down in textbooks reflects the limitations of observers embedded within a computation they cannot outpace.
That's a compelling argument, but have you considered the cost of that perspective? Reducing the second law of thermodynamics entirely to our computational limitations strips physics of its tangible reality. If you are saying that entropy only increases because our brains are computationally bounded, you are essentially saying that the arrow of time, the burning of stars, and the eventual heat death of the universe are just artifacts of human cognition.
I think artifacts is the wrong word. They are macro-scale realities born from micro-scale computations.
But let's ground this. If a tree falls in a forest and no computationally limited observer is there to fail at decoding it, does entropy still increase? The physical reality of heat transfer and energy dissipation operates independently of whether an observer believes they persist through time. By arguing that physics merely reflects observer limitations, we are ignoring the mind-independent physical reality of the universe in favor of a theoretical, purely computational framework. It is an elegant mathematical philosophy, but it risks reducing the tangible physical universe to a mere byproduct of our own cognitive boundaries.
Wait, let me stop you there because that is exactly the power of the concept. It does not render the universe a byproduct. It redefines what the reality of the universe actually is. You bring up a star burning out as if it is an independent physical truth completely separate from computation. The material posits that the star, the heat, the energy, these are all manifestations of the rule-based rewriting of the atoms of space.
But we measure the heat, we measure the continuous transfer of energy.
Yes, because the thermodynamics we observe is the macro-scale translation of that micro-scale computation. We cannot observe the individual updating of the relationships between the atoms of space, just as a fluid dynamicist cannot track every single molecule of water in a turbulent river. We aggregate. We average. And our averaging, born from our computational limits, creates the continuous physical laws we perceive. The framework doesn't strip physics of objective reality, it provides the actual objective reality, the discrete rules, and explains why we see the subjective reality of continuous physical laws. It is a unifying theory that elegantly explains why our continuous mathematics works at a macro level, but fundamentally breaks down when we try to understand the irreducible complexity of the universe at a quantum level.
I understand the elegance of that unification. It's a beautiful idea. But elegance does not automatically translate to physical truth. History is replete with beautiful mathematical models that did not map onto reality. You mentioned that traditional continuous mathematics breaks down, but let's remember the incredible predictive power of continuous frameworks in physics. General relativity models spacetime as a continuous manifold, and its predictions have been verified to extraordinary precision.
True, but it notoriously fails to integrate with quantum mechanics.
It does. But let's look at the analogy from the text again, building walls from irregular rocks. As we agreed earlier, it perfectly describes biology. An organism is a messy aggregate of evolutionary hacks.
A neural network is a mathematically messy web of weights and biases that we cannot easily dissect. But space-time does not behave like a wall of irregular rocks. The laws of physics at the macro and micro scales exhibit profound symmetries and conservation laws that are highly regular. To claim that beneath this extreme regularity lies a discrete, computationally irreducible graph of spatial atoms is to force a biological and algorithmic paradigm onto a physical domain that hasn't asked for it.
It hasn't asked for it yet. Physics is currently stalled precisely because it refuses to let go of the continuous manifold. You bring up general relativity, which is perfectly continuous. But why does it conflict with quantum mechanics? Because quantum mechanics introduces a granularity, a discreteness to energy and matter that a continuous space cannot easily accommodate. By proposing that space itself is discrete and made of relationships between atoms of space, the computational framework naturally generates the discreteness we already observe in quantum systems.
But what about the symmetries I mentioned? How do you get perfect symmetry from irregular, chaotic rule rewriting?
That is the beauty of simple rules. Simple rules, when applied millions of times, can produce large-scale symmetries. We see this in cellular automata. Think of a simple grid on a computer screen where squares change color based on the state of their neighbors. Those are extremely simple, discrete, and deterministic rules, yet they can generate perfect nested fractals and symmetric patterns. The regularity of the universe does not preclude a discrete, irregular, rule-based foundation. In fact, if we accept that we are computationally bounded observers who believe we persist through time, the very act of our observation filters the computational chaos of the Ruliad into the smooth, symmetric laws of physics we perceive.
But this relies on a massive assumption that our perception of continuity is just a low-resolution rendering of a discrete reality. You mentioned cellular automata. They are fascinating, but let's think about how they actually work. They run on a grid. They have a predefined spatial structure, and crucially, a universal clock that updates every cell simultaneously. If the universe operates through rule-based rewriting of spatial relationships, how does a step-by-step process execute without objective time? Who or what keeps the clock?
That is a fundamental question, and the material addresses it directly. The updating of the network, the rewriting of the rules, does not happen according to a universal clock in the background.
Then how does a step in a computation actually occur?
The updates are time. Every time a relationship between atoms of space is rewritten, a quantum of time has elapsed in that local region of the network. Time is not a container in which the computation happens. Time is the computation itself unfolding. Relativity emerges naturally from this precisely because different parts of the network can update in different sequences, depending on the observer's path through the Ruliad. Because we are computationally bounded, we cannot perceive the myriad individual causal updates, so we experience them as a continuous flow of time. It is a completely self-contained logic. The computation generates both space and time simultaneously.
If time is merely the local updating of network relationships, and we can only experience this as a continuous flow because we are computationally bounded, then we return entirely to my earlier concern about making human limitation the center of the universe. The vast, expanding cosmos is reduced to a byproduct of our inability to process information fast enough. While I appreciate the rigorous consistency of the argument, I must emphasize that a universe built entirely out of discrete computational rules and observer limitations is a universe that has been reverse engineered from computer science rather than observed from nature.
I don't see it as reverse engineering. I see it as finally finding the right vocabulary.
But look at the history of science. We have consistently taken the most successful tool of our current era and cast it in the role of the fundamental reality. Centuries ago, we thought the universe was a clockwork mechanism because clocks were the pinnacle of our technology. During the Industrial Revolution, we thought of it as a thermodynamic engine. Today, because we are surrounded by artificial intelligence and algorithms, we are projecting computation onto the very fabric of space. We are taking the irregular rocks of our current technological era and insisting the whole universe is built out of them.
I hear that historical critique, but I'd argue we project computation today because computation is the first paradigm that successfully encompasses all the others. The clockwork universe couldn't explain thermodynamics. The thermodynamic universe couldn't explain the intricate complexity of biological evolution, but the computational universe naturally yields both.
It yields models of them, certainly.
It yields the reality of them. We must summarize our positions now as our time draws to a close. My stance remains that viewing reality through the lens of the Ruliad and discrete computation finally unites biology, artificial intelligence, and fundamental physics under one logically consistent roof. It provides a cohesive explanation where the apparent randomness of nature and the inevitability of the second law of thermodynamics are directly driven by our limits as observers interacting with the profound reality of computational irreducibility.
And my summary is that while computational irreducibility is an absolute masterpiece of an explanation for evolving biological systems and the black box nature of artificial intelligence, taking that same framework and declaring the fundamental fabric of continuous space to be discrete computational atoms risks mistaking a highly effective map for the territory itself. It projects an algorithmic model onto objective physical reality, elevating a tool for understanding our limits into a fundamental truth about the cosmos.
Despite our deeply held differences on the fundamental nature of space and physical laws, it is clear we share common ground. We both recognize that computational irreducibility fundamentally changes how we must look at complex systems. Whether we are trying to decode the latent space of a neural network or understand the irregular, survival-driven rocks of evolutionary biology, the realization that some systems simply cannot be shortcut is a profound leap in human understanding.
I agree completely. The framework has forever altered the lens through which we evaluate complexity. We respectfully remain at odds over whether this framework defines the literal foundation of physical reality and the true nature of entropy, but the utility of the concept in the realms of biology and machine learning is undeniable.
The value of viewing reality through multiple analytical lenses cannot be overstated. We encourage everyone listening to explore the source material further, to wrestle with the concept of the Ruliad, computational irreducibility, and the fascinating implications of our own observer limitations themselves.
Indeed, there is much more to uncover in the material.
We will leave it to you to weigh the evidence and draw your own conclusions about the computational architecture of universal complexity. Thank you for joining us on The Debate.
Welcome in. It's incredibly good to have you here with us today.
Yeah, really glad to be diving into this one with you.
Because on this show, we spend a lot of time sifting through complex ideas, looking for those massive foundational shifts in how we understand the world. And if you are listening to this right now, I know exactly the kind of learner you are. You aren't here for the surface level summary. You don't want a neat little list of disconnected facts to memorize.
Right, you're looking for the bedrock.
Exactly.
Yeah.
You want that specific, thrilling feeling of a massive aha moment where the pieces finally click together and you get a sweeping panoramic view of the big picture.
And today, we have something that I think is going to deliver exactly that.
We really do. We are immersing ourselves in excerpts from a profoundly challenging text titled The Computational Architecture of Universal Complexity. It details theories put forward by Wolfram. And our mission today is ambitious. We're looking at a framework that attempts to completely rewrite the operating system of how we perceive reality.
It really is a sweeping piece of work. When we approach a text like this, we have to be prepared to abandon some very deeply ingrained assumptions.
Yeah, which is never easy to do.
No, it's not. For centuries, the prevailing consensus in science and philosophy has been that mathematics is the language of nature. We are taught that the universe is this vast physical thing, and mathematics is the human tool we use to describe it.
Right.
But the foundational premise of this text flips that entirely on its head. It proposes that the universe isn't just described by mathematics. It argues that the universe is, at its fundamental literal core, made of computation.
Okay, I have to stop you right there because that is a massive claim and it immediately brings up a red flag for me.
I figure it might.
Yeah, because when we say computation in our daily lives, we usually mean a process running on something. A software program runs on a silicon microchip. A thought runs on a biological brain.
Right, the hardware.
Exactly. If the universe is computation, what is the physical hardware? You can't just have software running on absolutely nothing, can you? It feels like we were playing fast and loose with the word computation here.
That is exactly the conceptual hurdle the text wants us to confront first. Our human intuition strongly insists on a substrate. We demand to know what the metal is.
Right, we want something to touch.
But the author is asking us to strip away that bias. In this framework, computation isn't an activity happening to a physical material. The application of rules is the fundamental ontological reality.
Meaning the rules are all there is.
Basically, yeah. When we say computation here, we mean the relentless, iterative application of simple rules. You take a starting state, you apply a rule, you get a new state.
Okay.
You take that new state, apply the exact same rule, and get another state. The text argues that this process, the pure execution of rules, doesn't need a host substrate because is the substrate. It's what everything else is built out of.
Okay, let's ground this. Because the distinction between math describing reality and computation being reality is the hinge for everything else we're going to talk about today. Let's look at the analogy of a tree.
I love this analogy.
If I want to understand a tree, I can use mathematics to describe it. I can calculate the angles of the branches, the fractal patterns of the leaves, the arc of the trunk against the wind. I can write a beautiful equation that represents that tree.
You can.
But that math is fundamentally a passive description. The universe isn't looking at my equation to figure out where to put the next leaf.
Precisely. Mathematics in that context is an observer's summary. It's a top-down description of a finished product.
Right. But computation, as the text defines it, is generative. It's bottom-up. It's like the genetic code inside the seed of that tree.
Yes, exactly.
The DNA doesn't contain a tiny blueprint or a mathematical equation of a fully grown oak. It just contains a set of rules for protein folding and cell division. The code is an active, running process.
It takes nutrients from the dirt, applies the rule, splits a cell.
Applies the rule again, splits another cell.
Yeah, it executes step by microscopic step until eventually a massive, complex tree emerges. And the text is arguing that this isn't just how biology works, it's how everything works.
Everything, which is wild.
And that brings us to the sheer, staggering scale of the proposition. The author points to 3 completely distinct domains of human study and argues that this exact same computational mechanism is the engine driving all of them.
Okay, lay them out for us.
First, biology, as you just beautifully illustrated with the tree. Second, machine learning and artificial intelligence. And third, physics itself.
Physics itself.
Yeah, the foundational bedrock of matter, energy, and space-time. The text connects a living cell, a modern AI chatbot, and the fabric of the cosmos into one cohesive computational framework.
But bridging those gaps requires us to accept something that feels very counterintuitive. Because if we look at a biological ecosystem or the output of an advanced AI or the collision of galaxies, we're looking at systems of unfathomable complexity. The natural human assumption is that complex results require complex origins. If I see a sophisticated machine, I assume there's a massive, highly complicated blueprint somewhere.
We all share that bias. We assume a 1-to-1 ratio between the complexity of the rules and the complexity of the output.
Right.
But the foundational revelation of this text, drawn from decades of studying computational systems, is that this intuition is entirely false. Extremely simple programs, rules so basic you could write them on a napkin, can and do produce behavior that is utterly unpredictable and wildly complex.
That feels almost like a magic trick. How does something simple create something complex without any added instructions?
Think about a rhythm. Imagine someone tapping a desk. Tap, tap, tap. It's a single rudimentary rule.
Okay, I'm with you.
Now introduce a second rule. Every third tap, a slightly offbeat syncopation joins in.
Yeah.
And then a third rule. Every fifth tap, the tempo shifts.
So it's building up.
Yeah, none of these rules are complex. They don't require a master composer to draft a symphony. But if you let those rules run, looping and layering over each other, within a few minutes, what started as a simple tap will intersect and compound into a chaotic, rich, deeply complex wall of sound.
Wow.
You didn't need a complex blueprint, you just needed simple rules and the willingness to let them run iteratively.
So if reality is just simple rules looping and layering, we completely eliminate the need for a master plan. The universe doesn't need to pre-calculate the swirl of every galaxy or the neural pathways of a human brain.
Right.
It just needs the starting rules and enough time to let the computation run. It's an incredibly elegant way to look at existence.
It really is.
But it leads to a very practical and frankly frustrating problem. If everything is based on these beautifully simple rules, why is life so relentlessly messy?
That is the big question.
Right. Why can't we easily predict what the weather will be next month, or how a specific disease will spread through a population? If it's all just deterministic rules, why can't we just look at the rules, solve the equation, and know exactly what's going to happen next?
Because you are looking for a shortcut, and the text argues that for the vast majority of the universe, shortcuts do not exist. This brings us to one of Wolfram's most critical concepts,
Okay.
computational irreducibility. It is the absolute blockade of prediction.
Computational irreducibility. I want to really unpack this for you listening, because once you grasp this concept, you start seeing it absolutely everywhere in your daily life.
To understand irreducibility, we first have to understand its opposite, a reducible system.
Okay, let's start there.
When we use traditional mathematics, we're usually dealing with reducible systems. Say, I want to know where a train traveling at 60 miles an hour will be in exactly 10 hours.
I remember this from high school math.
Right. I don't have to physically sit there, watch the train, and wait 10 hours to find out. I can use a mathematical shortcut. Distance equals rate times time.
So 60 times 10 is 600 miles.
Exactly. I bypassed the physical process, jumped ahead in time, and arrived at the exact answer in 3 seconds. I reduced 10 hours of physical reality into a simple equation.
We basically hacked the system to get the answer early. And because human engineering and classical physics are built on those kinds of hacks, we assume we should be able to do that with everything.
Exactly. We really do. But computational irreducibility dictates that for many complex systems, there is no mathematical shortcut.
None at all.
None. There is no magic formula that will let you jump ahead. The system cannot be reduced or simplified. The only possible way to know what the system will do at step 1 million is to let it run through step 1, step 2, step 3, all the way to 1 million.
Wow.
The system itself is its own fastest simulation. You cannot predict the outcome. You can only observe the process.
This is a profound shift in how we view the limits of human knowledge. The text points out 3 specific real-world domains where computational irreducibility is the defining characteristic.
Let's go through them.
The first one is incredibly relevant right now: neural networks and AI. We're living in an era where AI models can generate photorealistic video, write code, and pass medical exams. They work staggeringly well.
They do.
But if you ask the engineers who built these networks exactly how the AI decided to put a specific pixel in a specific place, they often can't tell you. It's famously called the black box problem.
And computational irreducibility explains exactly why that black box exists. A neural network isn't a traditional reducible software program.
Right.
The engineers didn't write thousands of if-then statements detailing how to draw a dog on a skateboard. Instead, they set up millions of simple rules, fed the system massive amounts of data, and let the computation run.
And it just figures it out.
The network applies those simple rules across billions of parameters, layer after layer. The complexity of the output emerges irreducibly. You cannot write a simple equation to summarize the internal logic of the network, because the sheer brute force computation is the logic.
You can't shortcut it.
No, you can't.
Which means we've built technologies that are as irreducible as nature itself.
Yeah.
We have created systems that fundamentally defy our ability to perfectly predict them.
Exactly.
And speaking of nature, that is the second major example in the text: biological evolution. When we look at something like the human eye or the camouflage capabilities of a cuttlefish, we're looking at staggering, intertwined complexity.
Yeah.
And human beings instinctively want to reverse engineer it. We look for the design. We want a tidy logical blueprint that explains why the organism functions the way it does.
But if biological evolution is an irreducible computation, searching for a top-down blueprint is a fool's errand. There is no blueprint.
Nothing at all.
No. There was no end goal in mind when evolution started. It just took the simple rules of genetic mutation and environmental selection, and it ran them step by step, organism by organism, over billions of years.
Incredible.
The complexity of the cuttlefish's skin wasn't planned. It was computed. You cannot shortcut evolution to see what it will produce in a million years, and you cannot reverse engineer its current products into a neat mathematical summary. The long, messy process is the only way to get the result.
The third example the text uses brings this right down to the physical world we interact with every day: natural randomness.
Yeah, this is a great one.
Think about watching water swirl and crash around a jagged rock in a river, or watching the unpredictable path of a hurricane. To our eyes, it looks entirely random. We throw our hands up and say it's just chaotic chance.
But the text is telling us that it isn't random at all. The water and the weather are strictly, perfectly following the simple rules of physics.
It's entirely deterministic.
It is entirely deterministic. Every drop of water is following a rule. But the interaction of all those drops applying those rules simultaneously creates irreducible complexity.
So it only looks random.
Right. It only looks random to us because our brains are desperately searching for a reducible shortcut, a way to predict exactly where the splash will land.
Right.
When we can't find the shortcut, we label it chaos. But the water isn't chaotic. It is just computing the next frame of reality. And the only way to know where the water goes is to watch it go there.
I really want you to think about how often we fight against this reality in our own lives. Think about how badly we want shortcuts for irreducible things.
We want them all the time.
We want the simple three-step formula for a perfect relationship. We want a neat, reducible economic theory that will perfectly predict the stock market. We want simple labels to explain the staggering complexity of human behavior. But this concept of computational irreducibility is a blunt reminder that sometimes no shortcut exists. You cannot squish an irreducible reality into a digestible textbook equation. You just have to let the program run.
But this does raise a fascinating friction point. If the universe, through evolution, and our modern computers, through AI, are both operating on this vast, irreducible scale, how does that contrast with how we, as human beings, actually try to build the world around us?
It's a great question.
Because human civilization isn't built on letting chaotic processes run for a million steps.
Yeah, we hate that. We love control. We love plans. And that brings us to what I consider the most brilliant and clarifying analogy in the entire text.
It's so good.
It is a direct comparison between human engineering and the computational universe. The text points out that both machine learning and biological evolution are essentially engaged in the same fundamental task. They are mining the computational universe.
Yeah.
They are running blind searches through an almost infinite space of possible rules and programs, looking for something that happens to achieve a goal, whether that goal is recognizing a face in a photo or surviving a drought.
The phrase mining the computational universe captures it perfectly. It's a vast landscape of potential rules, and evolution and AI are just digging through the dirt to see what works.
Exactly.
But the analogy the text uses to explain the results of that mining is crucial. It contrasts how humans build walls with how nature and AI build walls.
Right. The author says that traditional human engineering is like building a wall out of neat, perfectly identical bricks. But biology and AI build walls out of irregular rocks that just happen to fit together.
Let's deeply examine the engineering mindset first, the neat bricks. Why do humans build this way? When we build a brick wall or a suspension bridge or an airplane engine, we insist on uniformity.
We want perfectly straight lines.
We want straight lines, standardized parts, and clean mathematical models. We want a clean, isolated mechanism. And we do this because of our own computational limitations.
That makes sense.
We need a structure that our minds can easily comprehend and predict. If a brick wall starts to lean, an engineer can look at the clean, reducible geometry and calculate exactly which brick is failing. Our designs must be understandable to be useful to us.
We demand transparency. If I turn the steering wheel of my car, I can trace the mechanical linkage all the way down to the tires turning. It's entirely reducible.
Yes.
But nature, and by extension the AI we are currently building, doesn't care about our need for transparency. Evolution is not an engineer. It does not use neat bricks.
Not at all.
It reaches into the mud of the computational universe and pulls out jagged, bizarre, irregular rocks. It takes random genetic mutations, a weird protein fold here, a strange behavioral tick there, and it just shoves them together.
Right.
It doesn't care if the resulting structure makes logical sense. It only cares about the output. Does the organism survive? It builds a wall out of chaotic, irregular rocks, and if that wall stands up to the environment, the genes get passed on.
And neural networks operate on that exact same principle. When engineers train a massive language model, they are not writing clean, logical code that says, if the user asks a question about history, access the history database.
Which is what we're used to.
Yeah, but that's not what's happening. They are throwing terabytes of raw text at the system and letting it adjust billions of jagged, irregular internal parameters through trial and error. It shoves these mathematical rocks together until the output closely matches human language.
But isn't there a massive danger in building things this way? Because the result of building a wall out of irregular rocks is that you get a structure that is incredibly robust, highly adaptable, and incredibly effective. Evolution produced the human brain, which is vastly more capable than any neat brick-built computer we've ever engineered.
Oh, very true.
But the catch is that the rock wall is fundamentally unexplainable. You look at thousands of weirdly shaped stones perfectly locked together, and you have no idea how to explain its structural integrity. It defies human logic. It just
Yeah.
works.
And this is the root of the intense anxiety surrounding AI alignment today. We have stumbled into a method of creation that mirrors nature. We are growing complex systems rather than engineering them.
Right.
But we still expect them to behave like human-engineered machines. We want our AI to be perfectly understandable, transparent, and predictable like a brick wall. But we built it using irregular rocks.
Yeah, that's exactly it.
The anxiety stems from the realization that we are deploying systems whose fundamental architecture is computational, irreducible, and therefore permanently opaque to us. We have invited something into our world that operates on a level of complexity we cannot natively parse.
That is a deeply unsettling but necessary realization. If we want the astonishing power of irreducible complexity, we have to surrender the comfort of complete engineered understanding.
We do.
But let's take this down to an even deeper level. If biological evolution and artificial intelligence are running these massive irreducible programs, hacking together irregular rocks to build complexity, what is the ultimate hardware? We touched on this earlier, but if the entire physical universe is just computation, what are the literal physical rocks that the rules of physics are operating on?
To answer that, the text takes us down to the absolute microscopic foundational layer of reality. It forces us to reevaluate the nature of space itself.
Okay, there we go.
Our default assumption, inherited from classical physics, is that space is continuous. We imagine it as a smooth, infinite void, like a perfectly smooth sheet of rubber. You can cut a continuous space in half and cut that half in half, and you can keep zooming in infinitely forever, and it will always just be smooth space.
Right. There's no bottom to continuous space. It's infinitely divisible.
Exactly. But the text proposes a radical alternative. Space is not continuous. Space is discrete.
Discrete. Let's make sure we have a solid grip on that concept.
Instead of a smooth sheet of rubber, imagine looking very closely at the screen of your television or your smartphone. From a distance, an image on the screen looks perfectly smooth and continuous. But if you zoom in close enough, you see that the image is actually made up of millions of individual distinct pixels. There is a fundamental, smallest possible unit of the picture. You cannot cut a single pixel in half and still have a picture.
I see.
The text argues that the universe operates the same way. Space is quantized. It is fundamentally made of a vast network of discrete, indivisible nodes. Atoms of space.
Atoms of space.
Yes.
So space isn't an empty room that things happen inside of. Space is an actual structure made of these microscopic connection points. But those nodes aren't just sitting there frozen in a static grid, are they?
No, and this is where the computational engine of reality kicks in. The universe is defined by the relationships and connections between these discrete atoms of space.
Okay.
And the fundamental simple rules of the universe are constantly acting upon these connections through a process the text calls rule-based rewriting.
Rule-based rewriting. It sounds like a word processor finding and replacing text in a document.
The analogy is surprisingly accurate. Trillions upon trillions of times a second across the entire cosmos. The underlying rules examine the local network of space atoms. They look at how they are connected. They apply the rule, which breaks certain connections and forms new ones. The network is continuously rewriting its own geometry.
Wow.
Movement, gravity, particles. In this model, a physical particle isn't a solid ball moving through the nodes. A particle is a specific, tangled pattern of connections. And as the rules rewrite the network, that specific pattern shifts from one group of nodes to the next.
It's like a digital marquee sign.
Oh, that's good.
The light bulbs themselves don't physically move across the sign. The system just turns certain bulbs off and certain bulbs on in a sequence. And to us, it looks like a word is moving across the board. In this model, physical matter moving through space is just a pattern of connections being rapidly rewritten across the discrete nodes of the universe.
That is a phenomenal way to visualize it. Space is constantly updating itself, computing its next state.
But this inevitably leads to the ultimate question. If the universe is a massive network of nodes updating based on rules, what are the rules? Is there one master equation? Is there a single final rule that governs our specific universe?
And this is where the text introduces what is arguably the most mind-bending sci-fi concept of the entire framework. It introduces the concept of the Ruliad.
The Ruliad.
The Ruliad. To understand this, we have to stretch our imagination to the absolute limit.
I'm ready.
We've talked about simple rules like, if 3 nodes connect, break 1 connection. Now imagine every single possible rule that could ever be conceived, every variation, every permutation. The text defines the Ruliad as the entangled structure of all possible computational rules, running all possible initial states, generating all possible outcomes.
Wait, all of them simultaneously?
Simultaneously. It is the ultimate limit of computation. The Ruliad is an abstract, infinite structure where every conceivable computational process is happening at once. It is a structure of absolute pure computation.
Okay, my brain is hitting a processing limit here. If the Ruliad is this infinite entanglement of every possible rule computing every possible outcome, it sounds almost like the multiverse theory.
It does, but it's different.
But how does that relate to us? Where do you and I and the listener and the Earth fit into an infinite web of every possible rule?
Right.
Why do we experience this one specific, seemingly stable reality?
That is the crucial distinction. The Ruliad isn't a collection of separate universes floating in bubbles. It is one single, unimaginably vast, entangled structure.
Okay.
And the text provides a profound conclusion regarding our place within it. We as observers do not stand outside the Ruliad looking in. We are embedded inside it.
Right.
But because we are finite, physically limited entities, we only have so much brain mass. We process information at a finite speed. We cannot possibly perceive the entirety of the Ruliad. We only have the capacity to sample a tiny, minuscule fraction of it.
We are taking a thin slice.
Exactly. We are a thin slice through the Ruliad. We are tuned into a very specific, narrow frequency of computational rules. And that tiny, specific slice of the infinite computation is what we call our universe. It's all we can see.
We are essentially looking at an infinite, multidimensional tapestry through a microscopic pinhole. And everything we know about reality, the stars, the planets, human history, is just the tiny bit of thread visible through our specific pinhole.
And this implies something incredible about the nature of existence. If there were other entities or other types of observers with different computational capabilities or different physical structures, they might take a completely different slice through the Ruliad.
They would see a different reality.
They would experience a completely different set of physical laws, different dimensions, a totally different reality, but they would be existing in the exact same underlying Ruliad as us.
This perfectly tees up the final and perhaps the most earth-shattering question of this entire deep dive.
Let's hear it.
If the universe is just this massive, infinite web of computational rules updating discrete pixels of space, and we are just looking at a tiny slice of it, why do our specific physical laws feel so rigid and real?
Yeah.
Why does gravity pull us down? Why does time seem to only move forward? Why does my coffee get cold if I leave it on the counter? If it's all just abstract computation, why does physics work the way it does?
It is the ultimate question. If the universe is just computation, where does physics come from? The text's final major revelation is a complete paradigm shift regarding how we view the laws of nature.
Okay.
It argues that the laws of physics, as we experience them, are not fundamental, independent truths of the universe. Instead, physics is largely a reflection of the limitations of the observer.
So you're saying physics is essentially a symptom of us being limited, that the laws of nature aren't out there in the void, they're artifacts of how we process information.
Yes. The text identifies two specific fundamental traits that define us as human observers embedded within this computation. Trait number one, we are computationally bounded.
Meaning our brains and our scientific instruments only have so much RAM. We have a processing limit.
Exactly. Remember the discrete atoms of space and the rule-based rewrites happening trillions of times a second?
Yeah.
We cannot perceive that. We are far too massive, far too slow, and computationally too weak to track the individual microscopic computations of reality. Because we can't see the tiny details, our brains coarse-grain reality. We average things out.
We blur it.
We blur the trillions of discrete nodes into what looks like a smooth, continuous physical object. Our first limitation is that we only see the macroscopic blur, never the microscopic precision.
Okay, that makes sense. It's like looking at a massive pointillism painting. Up close, it's just millions of distinct dots of paint. But we can't process all those dots at once, so we step back, our eyes blur the dots together, and we see a sailboat.
That's a great example.
The sailboat is a coarse-grained illusion created by our visual limits. So we are computationally bounded. What is the second trait?
Trait number two, we believe we persist through time.
Wait a minute. We believe we persist. I do persist. I was here an hour ago. I am here now. I have memories of yesterday. I am a continuous entity moving through time.
You experience it that way. But let's look at it through the computational model. Space and everything in it is constantly being rewritten by rules, frame by frame, moment by moment.
Right, the marquee sign.
You are not physically the exact same pattern of space atoms that you were 1 second ago. You have been computationally updated. However, your biological brain has memory. It weaves those consecutive, discrete, updated states together into a single, continuous narrative thread. You stitch the frames of the movie together to create the illusion of flowing motion. You believe you are a single, persisting entity experiencing a linear flow of time, when in reality you are a sequence of computational states.
Okay, so we had these two traits. We are computationally weak, so we blur things together, and we stitch moments together to create the illusion of continuous time. How do those two human limitations literally create a law of physics?
Let's take an example.
Because the text specifically tackles one of the most unbreakable laws in science, the second law of thermodynamics, entropy.
Entropy is the perfect case study for this framework. The second law of thermodynamics dictates that in a closed system, entropy always increases. Things naturally degrade from order into disorder and randomness.
Right.
A glass shatters, but shards of glass never spontaneously assemble into a perfect cup. A drop of ink spreads out in water until the water is totally cloudy, but cloudy water never spontaneously separates back into a single tight drop of ink.
Right. It's the arrow of time. It's the universe getting messier.
Classical physics says this happens because the universe is fundamentally random at the microscopic level, and there are far more messy states than orderly states. But remember what we established earlier, the computational universe is deterministic.
Right. There is no actual randomness.
There is no actual randomness. Everything is simple rules running irreducibly.
Right. The swirling smoke from the campfire. It looks random, but it is strictly following rules.
Exactly. So if the universe is strictly deterministic, why does entropy appear to be a universal, unbreakable law? The author argues that entropy increases strictly because of our first observer limitation. We are computationally bounded.
We can't decode the computation.
Precisely. Let's look at the ink drop in the water. You start with a highly ordered state, a tight, perfectly round drop of black ink. To our limited brains, this is simple. It's low entropy.
Easy to understand.
As the underlying rules of the universe compute the interactions between the ink and water molecules, the ink spreads out. After an hour, the water is a uniform, messy gray. To us, it looks like the system has degraded into chaotic randomness.
Yeah, you can't undo that.
But the text argues that the final gray state is not random at all. It is the exact deterministic output of millions of microscopic rule applications. The information of that perfect initial drop of ink hasn't been lost or destroyed.
It's still there.
It is still perfectly encoded in the... It is a physical reality for an observer with your specific limitations. The text isn't denying that the glass shatters. It is saying that the shattered glass contains the exact same amount of fundamental computational information as the intact glass.
Okay.
The disorder is entirely relative to your capacity to understand the new arrangement of the atoms of space.
This is a monumental paradigm shift. It means the messiness of the universe, the relentless degradation of order, the arrow of time itself. These are not cold, hard mandates handed down by the cosmos.
No, they aren't.
They are artifacts of our specific way of observing. Because we string time together in a straight line, and because our brains cannot possibly compute the vast, staggering complexity of the rules acting on discrete space, we perceive physical laws, gravity, relativity, thermodynamics. The laws of nature are essentially a mirror. They're reflecting our own biological and computational limitations back at us.
That is the profound beauty of this entire framework. We are no longer looking at a universe out there that forces arbitrary mathematical laws upon us. The universe is just pure computation.
Laws.
The laws are merely the interface our minds create to interact with that computation. The text fundamentally argues that if you change the observer, if you alter their computational limits or how they perceive time, you literally change the physics they experience.
I want to make sure we connect this directly back to you listening to this right now. Because when we spend an hour talking about the infinite Ruliad, discrete nodes of space, and the computational irreducibility of the cosmos, it can start to feel very abstract.
It definitely can.
It can feel disconnected from your daily life, from your commute, from your work. But think about what this framework actually means for your place in the world. It is incredibly empowering. You can walk outside today, look up at the clouds, or watch a leaf falling from a tree. You don't have to look at those things as cold, unapproachable mathematical equations that are disconnected from you.
No, you don't.
You can look at them as a beautiful, actively running program. That falling leaf isn't just passively obeying a static law of gravity. Its path is being actively computed, relationship by relationship, across the discrete fabric of space. And you are made of the exact same computation.
Yes.
You are embedded inside the program, witnessing it unfold from the inside.
It erases the hard, artificial boundary we've drawn between the observer and the observed. We are made of the exact same computational rules as the stars, the biological ecosystems, and the neural networks. We are just specific, localized structures within the vast Ruliad, experiencing our unique slice of the whole.
We have covered an immense amount of ground today. Let's briefly synthesize the journey we've just taken. We started by dismantling the idea that math describes the universe, replacing it with the profound concept that the universe is a generative computation drill. Simple rules looping to create staggering complexity across biology, AI, and physics.
Then we hit the wall of computational irreducibility, realizing that the chaotic unpredictability of life and nature isn't randomness, it's just a process that cannot be shortcut.
We explored the friction between human engineering and natural complexity. We construct our world with neat, reducible bricks. But evolution and AI mine the computational universe for irregular rocks, building opaque but incredibly robust structures.
We dove down to the bedrock, looking at space not as an empty void, but as a discrete, quantized network of relationships constantly rewriting themselves. We glimpsed the staggering infinity of the Ruliad, the entanglement of every possible rule.
And finally, we turned the lens back on ourselves, realizing that the unbreakable laws of physics, like entropy, are simply the universe reflecting our own computational limits back at us.
As we conclude this deep dive, I want to leave you with one final provocative thought to mull over. We've established that our physical laws exist largely because we are computationally limited observers who only see the coarse-grained blur of reality rather than the microscopic precision of the rules.
Right.
So consider this. What if there was an entity or perhaps a future unimaginably advanced artificial intelligence that wasn't computationally limited?
Oh.
What if an observer came into existence that possessed enough processing power to actually track every single discrete atom of space and every single rule-based rewrite in real time? If something could perceive the entirety of the Ruliad at once, without the limitation of a physical brain, and without the illusion of persisting sequentially through time, would the laws of physics as we know them instantly cease to exist for that entity? Would they step completely outside of thermodynamics and the flow of time, existing in a state of pure, crystalline computation?
A universe without physics, where the observer sees the code itself. Now that is a thought to keep you awake tonight. Thank you so much for joining us and lending us your time and your curiosity. I hope you found that perspective shift you were looking for. Keep questioning the fundamental nature of things. Keep seeking out those big picture connections, and keep looking at the world around you as the ultimate unfolding computation. We'll catch you next time.